Okay, so we're going to proceed to uh, look at normal QQ plots to check for normality of a distribution. All right, and the reason is that the methods that we just did rely on relatively vague judgments about what is close enough to be considered normal. So we can do that in a somewhat more objective manner. It's still not entirely black and white, but we can, using what's called a normal quantile plot. It's also called a normal QQ plot. So the data set we're looking at is the body data, data set number one. And let's actually take a quick look at that. So I'll flip over to Excel. So that was this uh, Excel spreadsheet where the individuals are broken up, or their data, their gender, pulse, and so on are recorded. So I've initially sorted it by gender. So all the women are the first 150 rows or so. So we're looking at the weights. So it's the weight column here. So what we'll do is we'll select all these weights, and I'll stop when the gender switches to 1. So that was there. And I'm going to just copy those. So just copy that. And I'm going to paste it into a new tab just to keep things a little bit tidier. So I'm going to call that weight. Okay, it didn't quite work. Let's see. Control C. Okay, so that's the weight of my 147 subjects, all female. And first thing I'm going to do is I'm going to sort them. So I'll select that column and I'll go over to I'll hit the data tab, data, and sorting is here. So I can go through the dialog here, sort by weight. Yes, that's what I want. Okay, so the lowest weight I'm just shocked that there's one that's 39. So I wonder if this is kilograms. This must be kilograms, right? Because 39 is very, very low. Okay, and it goes up to 150. Yeah, so the largest is 150, so that must be kilograms. So if we're right. Okay, now let's just think about the basic idea for a QQ plot. So let me just put it like this. A QQ plot is a way to directly compare a given set of data to a normal distribution. It's essentially a direct comparison, and by seeing how well they line up, we can see whether that original data set is normal. So what we need to do is we're going to, from the given data, we're going to generate a set of Z values that come from a normal distribution. And as we'll see, we're going to be able to check if those Z values line up in the right way with the original data. So that's what we're going to do. We're going to produce a whole bunch of Z values, one Z value for each of the original data points. And then we're going to plot them and see if they form a line. Okay, so the first thing to think about here is that the weights of these 147 women, if I sort them, the sorted weights, then they divide up the space of possible weights. So let's imagine it like this. So let's say weight number 1 is the lowest one, and weight number 2, weight number 3, and weight number 4, and then it goes all the way down to weight number 147. And now what I'm imagining is that the space in between those values is what we'll call a quantile. So it's like a percentile where we're dividing up the space of possible weights into intervals that are all equally likely. Let me say that again. So remember that a percentile means it's a 1%. A percentile, the difference between one percentile and the next percentile is that 1% of individuals fall between those two values. Let me try that again. If you have two percentiles, let's say P50 and P51, those are two measurements where 1% of individuals are in between those. Quartiles are numbers where from the first quartile to the second quartile, 25% of individuals fall into that gap, and the next quartile contains the next 25%, and so on. So we're doing the same thing here. We're dividing up the space into gaps. These quantiles, they're called. That's the kind of general term for anything like this. Quantiles which contain approximately equal numbers of women. And now this is only an approximation, but and what we do is we also imagine that there's one quantile that comes before the first weight and another quantile that comes after the last weight. So this would be the first quantile, this would be the second, third, all the way up to, this would be the 147th quantile, and this would be the 148th quantile. So we're imagining that the lowest a weight could possibly be is that. That would be the lowest possible, and the maximum possible would be at the other end. So this may or may not be true, but it's a reasonable choice, a reasonable assumption to make. Okay, so we're imagining that if I sort the weights, they divide up the space of possible weights into these equal quantiles. Okay, so let's say that you could say, for instance, that the third woman, that would be her, the third woman is heavier than the first three quantiles, right? First three quantiles. Her weight is more than the first three quantiles of women, which puts her at what? So that would be 3 out of 148 quantiles, which is how much, what fraction would that be? Get my calculator out. What is 3 divided by 148 is 0.02027, 0.02027, which if we shift the decimal point, that's 2.027%. In other words, the weight of this third woman, W3, equals the second percentile, or 2.02 percentile. Okay. Now what? Now we're going to ask ourselves, if these weights actually followed a normal distribution, what would the weight, okay, let me just draw this first. Let's put it this way. For a normal distribution, in fact, for a standard normal distribution, where would the 2 percentile be? Oh, I rounded this off incorrectly, 2.03. That's right, this is right. Where would the 2.03 percentile be? Well, it would be P 2.03. It would be somewhere along this z-axis. And what would be true about it would be that this area, the probability to the left would have to be 0.020, well, may as well just use the exact number, 27. And what is that? What would that be? So, in other words, what would the z-score be for an individual who is at the 2.03 percentile? What would the z-score be? What would the z-score be for a woman whose weight was at the, oops, this needs to go away, whose weight was at the 2.03 percentile? weight for all women, assuming that weight was a normal distribution, assuming that the women's weights followed a normal distribution, that weight was normal. That's what we're asking ourselves. And the answer is that Z is norm dot S dot inverse of 0.02027 bracket, which is what? Let's see, what does Excel tell me here? Equals norm. In fact, here's what I'm going to do. Woman number 3, here's woman number 3 right here. Let's do the calculation in actually the right place. So here I'm going to call this percentile, and here I'm going to call it the Z-score. So for the third woman, what percentile is she? She was going to be equals 3 out of 148. So there's the percentile. And here I should have equals norm.s.inverse of 0.02027. So the Z-score is negative 2.0482. Negative 2.0482. Negative 2.0482. Okay, so why did I pick the third woman? That was just because then I could see in a bit more of an obvious way how many quantiles there were. Now, if we complete the picture, so let's go on. To make a normal QQ plot, we calculate the predicted Z-score for each woman in the sample based on her percentile. So I need to actually go here, I need to fill in both of these columns all the way to the bottom. I'm not going to do it manually. What is the percentile for the first woman? How many quantiles is she above? Well, just one, right? The first one. So it's 1 out of 148. Next woman is 2 quantiles, so equals 2 out of 148. Now, what's a better way to do this rather than just typing every quantile in? What I can do, instead of typing in the number 2 over 148, what I'm going to do is I'm going to say it equals B2, that's the first quantile, plus, so what do I have to add to go from 1 over 148 to 2 over 148? I just have to add 1 over 148. So that's the, and then if I copy this, Control C, Control V, okay, now I've got the third percentile, which is the 2.03% that I had before. So I'm going to be able to just copy and paste these all the way down. This formula, so for the Z-score, instead of typing in the percentile, I'll use a cell reference, norm.s.inverse. I need to refer that to cell B2. That's the percentile. Now let me copy that here. Okay, so what I can do now is select those, drag this corner all the way to the bottom, and I'll be done. Okay, so these, in the last column, these are the Z-scores. Let's just say it one more time. This number, for example, that's the Z-score, as in the number of standard deviations away from the mean. This is the Z-score that this woman, who was 79 kilograms, this is the Z-score that she would have if weights were exactly in a normal distribution. Okay, so what we're going to do next is we're going to say, let's see, let's go back to our checklist here. So we have just done that. We calculated these predicted Z-scores for each woman. We're then going to plot her actual weight as the X coordinate and the predicted Z-score as the Y coordinate. And they should line up. So here's what I do. I can click this column. I want to select the first and the last column. One easy way to do that is if I use the control button. So if I hit control and then click the third column, now I've got them both. So let me show you again. So I clicked A, Control, hold it down, click the C. Got it? Now I want to insert a scatter plot. So I'm going to insert a chart, and it's going to be this type scatter. And what do I get? So what I've done, I'm just a little concerned that looks different from what I previously did. Let's just think about that, why that would be. One moment here. Okay, I see what happened. So earlier when I was making this plot, I actually plotted the height here by accident, and that was in centimeters. So this, what we've just produced in Excel here is not the same. That's totally fine. This is actually the right one. So what have we done? We have produced this is what's called a normal QQ plot. It's called a quantile plot for let's call it 147 women's weights. And what do we have on the axes? So the vertical axis, I'll call that the z-score. Z-score, that's what the z-score of each woman would be if it was perfectly normal. And this is the weight axis. I'll call it the weight x in kilograms. And this is probably not obvious to you. I'm not sure if it's even obvious to me actually, but these should be a straight line. This should form an exactly straight line if the weights were normally distributed. Now, one way to see, it doesn't look that straight, does it? So one way to see this is if I click the plus button here, I can add what's called a trend line, this bottom one here, and it's super easy. I just click that, and now Excel will throw in a dotted line that it's the line that's the closest to the data, even though it doesn't lie exactly on the data. And so what we're going to do is grab this plot. So I'll just Control C that. Now you might notice the horizontal axis here with the labels, it's kind of cutting through the middle, and that's totally fine. It's just that the z-scores are, some of them are negative, so the dots are going below the x-axis. Now, so I was copying that, and I'm going to go back to my notes here. I'm just going to paste that right on top of this because, as I said, it's kind of the wrong graph. Okay, and let's try that one more time. The usual issue. Okay, now that worked. So what I should do actually is, okay, let's finish this exercise first, and then I'll tell you. Okay, so let's finish this. If female body weights were perfectly normal, then the scattered dots would lie precisely along a straight line. Every weight would line up exactly with the predicted z-score for that percentile level. Okay, now how well does this line up? Not that well, right? So these points at the beginning are well below the line, and then these ones again are also well below the line. So we have many points they lie off the line, off of the trend line. And the key things here, they are following a pattern. There's this kind of arc, this kind of overall arc to it, but it's not the right pattern. They're not following that line. A certain amount of scatter would be okay, but this is systematically deviating away from that line. So our conclusion here is going to be the weight, the dots in the normal QQ plot. Deviate in a systematic way, in an orderly way, systematic way from lying on the straight line. And what that tells us is that the data set is not normal. So that it has some kind of shape to it, but it's not normal, not normally distributed. Okay. Now, let's actually confirm that by looking again at the histogram. So in the previous video, which is still on the screen here, I showed this histogram. And I see what happened now is I in my mind, I was trying to convince myself that it was normal because I was thinking of this QQ plot, the one that I covered up that's underneath this one, which would show that it's normal. But that was the height data, not the weight data. If we look at this histogram, it is quite skewed, isn't it? I said it's roughly symmetric, but we should say it's actually noticeably skewed. And that's the reason why the data don't lie along the QQ plot line. Okay, so let's actually pull up that histogram again so we can manipulate it a little bit. This is it here, but let's just double check and make sure that's right. So let me go back to my weights here. So what I'm going to do is just select the weights. It's still column A. I'm going to insert a histogram. Histogram down here. Aha. And so that is the original histogram. I recognize it. Let's put a border around that so I can see it better. And let me change the number of classes. This is kind of a bit light on classes. Axis options. Let's see, we had 148 women. So what's the square root of 148? It's about 13, right? 12. Let's make that 12 bins. Yeah, and okay, that line is too thick. I don't like that. So let me change the border to be just a quarter of a point. And now this is the histogram of women's weights with n equals 148, 147. And now it's pretty obvious that this does have quite a sizable tail off to the right. So we'll call this the weight axis. This is the frequency. And that's good. So let's copy that. I'm going to paste that here in OneNote. And I'm going to grab that, cover this up, cover up my shame there. That's it's actually a little blurry. Let's see if I can make that bigger. And copy it again. Get rid of that. Okay. So there's my histogram of women's weights. And so there's this, I wanted a place for a final conclusion. Good. So what we notice in the histogram is that there is a significant right tail. So let's just see here. If it were to follow a normal distribution would sort of die off or would decay equally on both sides. So in other words, these weights are larger weights. Like the women at the higher end of the weight spectrum, they're larger in weight than what you would get in a normal distribution, larger than in a normal distribution. In other words, for that Z-score, so they have in other words, those women, um, let's quickly check the QQ plot before I finish that thought. So those women are at the, let's say, 130, 140 kilograms. That's these women here, right? And what we can say is that they are further along the weight. They're heavier. They're further to the right on the weight axis. They're more to the right than expected. Let's put it that way. So those dots should be on this line if it was normal, but they're all shifted to the right. So the right tail is heavier than you would expect for a normal distribution. Same here, actually. The women at the lower end are also heavier than you would expect. In other words, we're missing um, we're missing those women at the low end that we would expect to see. They're all pushed up towards the middle weights. Tricky, right? Okay, so the main thing to say here is that, okay, let's summarize it. So this distribution has a significant right tail, which makes it deviate from normality. And this shows up in the QQ plot. This shows up in the normal QQ plot as a shift to the right, shift to the right, shift to the right at the higher Z scores. At the higher quantile level, i.e. at the higher Z scores. At the higher predicted Z score levels. Maybe I should say 4 higher. Let's just look at that one more time. So for these dots where we expected Z scores of say 2 or 3, these ones do have Z scores of 2 or 3, but their weights are pushed to the right. Their weights are more than we expected. Okay, so I've just written this here. So this is the optional knowledge that you don't need to be able to demonstrate to me, which is to create the normal QQ plot. The interpreting part, I do expect you to learn that, but creating, not necessarily. And now we're only going to do it with Excel. And you will only ever do something like this with Excel or some other equivalent technology. You can ignore what the textbook says under the heading of a manual construction. I'm not going to do it manually. But what are the steps? First, we sort the data, and then we calculated those percentiles by adding multiples of 1 over n plus 1. So that was the width. That was the width of each quantile, assuming that the women were equally spaced in terms of the quantiles. 3. Then we calculated a predicted z-score for a normal z distribution using those percentiles. So that was using z equals norm dot s dot dist, no, dot inverse of, what was the percentile? It would actually be k divided by n plus 1 for the kth measurement. And then we plotted the predicted z values against the observed values. So then we plotted the z scores against the x's, and we looked for a straight line. So if you see the data mostly lying along a straight line, then that would shows that this variable x is normally distributed. Okay, so we'll leave it there. This is tricky, quite technical topic. I don't want you to get too anxious about the QQ plot. What you should be able to do is look at a picture like this and understand it enough to say, yeah, that's a normal distribution, because the QQ plot is nicely organized along a line. Whereas you look at this one and you say, that's not very straight. That's not a normal distribution. If you can do that, then you've achieved most of what you want to achieve. If you want to understand it at a deeper level, learn how to make the QQ plot, rewatch this video, try to understand why is it that a normally distributed data would lie along a straight line. That's a challenging one for you. Okay, so I will see you in the next video.